try to summarize also some of the projects that I worked on with Christos, and then I give an outlook what I did last summer when I was also on a sabbatical here in Crete. So join way with me, so I met Christos the first time in Vienna for a project that I will only briefly mention because I understand it's a little young, but also mention it a little bit. It's a huge project called S-Cube, and so the project then got funded, and from early 2008 on it was funded for years. It was a network of excellence, it was huge funding, but the EU wanted to bring together, how they call it, the lighthouse people in service computing, and Christos for sure belonged to. Next was a joint application for the EU because it was a so-called IMSE project, and most of the students are enrolled in the IMSE program. Then we successfully applied to another EU project called the Leymann project that Marina was mentioning. Then we also applied for a German Greek funding project successfully called ECHO. We also say a couple of words on it. We unsuccessfully, it's as Manuel said, right, it's always hard to be unsuccessful, but we all learned that in a reading proposal. I never understood why we didn't get funded, but if you get rejected, you never understand it. Then Christos and my institute worked together on a project here. You see, as also what Manuel mentioned, Christos was very open to new subject, and when I went to digital humanities, my colleagues in Germany said, Frank is going crazy. But he said, "Oh, that's a good idea. Digital humanities is fine." So so we cooperated a little bit, and Vasiliki also helped us right with the art capabilities. Thank you, Vasiliki. And then I was in a sabbatical in Crete, and I will mention that for some 10-15 minutes what Christos, Marina, and I did here in Crete. So this is the time I spent with Christos. So the S-Cube project was a project where we wanted to work out all methodologies how to develop scalable, large-scale service-oriented application. And Christos, Marina, and I worked on, and Yechiam Yemini, on refining service networks down to choreographies, down to business processes. And Christos really taught me what service networks basically are. I still enjoy them and have a thesis going on that works on service networks, a PhD thesis going on. IMSE, of course, Leymann mentioned it. Christos was not only a great researcher, but also a teacher, and he loved teaching, and he was easily convinced that we should set up a joint program with Tilburg University, Stuttgart, and Crete on educating young people in becoming service engineers. And the Alarm Ensemble project was something, well, when we had the first idea of a bio-inspired application architecture, right, and Marina already said the role that service networks and utilities play in this game, how cells find together and build organs, and so on. Marina already said a little bit what Christos did in this project, and what Marina is still doing. Next one was this digital humanities project, where I think Johanna will speak about it. So here's the main idea. We take the methodology that is established in natural sciences and apply that to humanities. And you will hear this evening that humanities hate us for this because they say this is not nature science, but we want to take care that they understand that humanities is doing it wrong. Right? The ECHO project was something that was fascinating. Yorgos and Christos convinced me to work on that. It's a healthcare application, especially in the area of lung diseases. Right? It's a project that we are still working on. It goes until the end of the year, and Christos really motivated me to participate in that. That it's a good idea, and then we talked together with Manolis and Yechiam Yemini, a major application that basically extended these ECHO ideas. And then he has a very nice photo. I know that Christos liked it too. We had a total ECHO meeting, and after that we made this selfie, and that's was very nice for us. So then came the sabbatical last year. So I have the great idea to rewrite architectures that software architects came up with, and based on pattern languages, we are going to rewrite the architecture based on knowledge that is captured in pattern languages. But I had a severe problem I didn't understand, because a pattern language, as you will see, has multiple solution alternatives, and I wanted to find the optimal solution. And Christos and Marina said, we can do it. It's based on the utility functions. All you need is to come to agree, right? And then I tell you how to do it. So it's a draft paper with Marina and Christos and Christoph, right? And I know, Marina, that I'm guilty to write it, so we have 15 pages, but I need to do a lot of teaching, and we are going to continue it. So here's a sample application, very simple application in this architecture diagram. Here you have a client, you have a server, and you annotate the architecture diagram with quality of service requirements, so the communication should be reliable, the server should be scalable and highly available, and we wanted to make use of pattern languages to rewrite this architecture, either manually or automatically. So the final goal is to do it automatically. And here you see a sample of a pattern language. Right, the pattern language has a bunch of nodes where you document proven knowledge of how to solve recurrent problems. And the edges basically say, okay, if you have this problem, you very likely also have this problem. And when you understood how this problem is solved, here is how you understood. Here is how you can solve the problem too. Right, so we all know scalability can be solved by a hot pool or by a load balancer. High availability has something to do with the watchdog and so on. So I'm coming back to this language here. Again, the pattern language in an abstract term is a graph, the nodes of which are the best practices, the proven solutions to recurrent problems, and the edges are links between the patterns that basically say, okay, they help you to navigate through the pattern graph to come to solve more complicated problems that need advice from different sources. So what you do is, the idea we had and that we worked on here in Crete was, well, you need an entry point to this kind of a pattern language. And here, if you remember, the application was saying, I need a reliable communication. So the entry point, the non-functional property reliability, points me to this pattern, and then the pattern basically documents how to make your communication reliable. And the pattern says, well, if you have the reliability problem, you can either implement it by transactional RPC or based on message queuing. And if you decide for message queuing, well, it's a good idea to think about, do you need at most once messaging or do you need guaranteed delivery in messaging? What you do basically is you navigate through the pattern graph, and in doing that, you create what is called a solution path. It's a crazy name, but it's an established name. So a subgraph in a pattern graph that is your solution of a complicated problem is called a solution path. Here we see the abstract stuff again. You have this directed graph, which is the pattern language. And if you have this problem, you need to solve this problem and this problem as well as this problem. So you have a connected subgraph of the pattern graph that describes how to solve a complex problem. So when we applied this reliability pattern, this reliability non-functional property, and then the pattern language basically said, well, it's a good idea to have reliable communication based on message queuing. So next, we come to the server, and the server says, I need to be scalable. Again, you go to the pattern language. Scalability gives you the entry to this pattern, and the scalability pattern says, okay, it's a good idea to have a hot pool. You don't need to understand what it is. And the hot pool could be implemented based on queuing or n-plexing, but we decided to go to queuing, right? So that basically means we have a hot pool of servers, so we've rewritten the architecture, we have a hot pool of servers, and the servers read their request messages out of the queue. Next, what's left over is the high availability requirement. So we go again to the pattern language, and the high availability entry point basically says, well, okay, high availability can be achieved by the hot pool and queuing. Well, we write this already, and in addition, you need a watchdog, whatever watchdog is. So basically, then the architecture is rewritten to add a watchdog to the server hot pool, and the watchdog can then measure, some of you may know that, the high availability of the system. So the main, and then of course the other idea that we had is, a pattern is basically an abstraction of proven solution, right? It is somehow abstract, but in order to implement the solution again, you have to do programming again. But because it's a proven, the pattern is a proven solution, at one point in time you had the actual implementation of a or many solutions. So the idea was not to forget the actual solution, which is currently done in pattern languages, but we also store and maintain the knowledge about the working solutions and tie them with the patterns. So if a pattern, if an architect needs to apply a pattern, then the architect can make a selection of one of the working solutions and, for example, grab a piece of code and basically use it. So this is what we then jointly here in Crete abstract. We basically define what a pattern graph with concrete solutions basically is, and I'm not diving into the details now, but I'm going into some of the details. So this was one of the first outcomes, the crisp mathematical definition of what the hell is going on if you have a pattern language connected with solutions. So here you see, for example, an example, guaranteed delivery can be implemented based on JMS, and here in the work that we are doing in Stuttgart, you have code fragments, how you implement guaranteed delivery in JMS, in MQ series, with Amazon SQS, and so on. Here you get an idea how we connect patterns with working solutions. The same is true for watchdogs. And then the question is, when you navigate through the pattern graph, because the pattern graph says if you have this problem, you also go to this problem, and you select a working solution here, and you select a working solution here, how can you aggregate the solutions? So the final idea is to navigate through the pattern graph, you grab working solutions, and then the vision, we are still not there, is to glue together the working solution into the working solution of the overall complex problem. Very hard problem. But it could be done, for example, here we have running prototype, you can glue together code fragments. Right? You have a code fragment, how you build hot pool based on MQ series, and you have code fragments, how to implement, for example, a hot pool. You can glue the code fragments together, and we already know the different domains require different operators, how you glue solutions together, and so on. This is ongoing work. It's not yet solved. Right? Here's now the refined pattern. Here's the pattern language refined with some solutions. Right? And if you want to glue solutions together, for example, if you say I build guaranteed delivery with MQ series, it doesn't make any sense then to build the hot pool based on JMS because it won't match. That means solutions always have pre and post conditions, and when you walk through the graph, you basically match the pre and post conditions in order to find out that the correct pieces of code, the correct solutions are basically glued together. But the real problem, why I came then to Christos and to Marina, was how can we compute optional path? Because up to now, architects need to go to the pattern language and make decisions based on their gut feelings, and we wanted to make that more rational. So how can we compute optimal solution path? How can we compute the optimal solution? How can we optimally aggregate it? And if we found the patterns that are applicable in my situation in an optimal manner, we also wanted to choose the best solutions. So how could we basically manage that? And here we basically said, well, the inventor of the pattern language must also define parameters that help me to make best decisions. For example, if you build a client-server architecture, what is always of interest is the response time of the overall system. Whether you need storage for the communication, whether you can tolerate denial of service attacks, for example. From this sample, basically said, okay, if you don't care about response time, but if you hate denial of service attacks, and if you're willing to pay for storage, then you can go to queuing. Or if you need fast response time, but if you maybe if you don't care about denial of service attacks and you are not willing to pay for storage, then you need to choose transactional RPC. This is what an architect also has in its guts, and here we try to formalize it, right? Add parameters to the edges in the pattern language that you can use to make real decisions. And the decisions, of course, not a surprise, could be done based on utility functions. This is what I learned from Christos and from Marina. So then Marina basically invented some utility functions. Here I learned that this is really an art and not a science, right? So Marina is a mathematical artist. Right, so she invented utility functions, and these utility functions could then be used to make decisions. So the edges are basically weighted, the edges of a pattern language are basically weighted, and the weights are basically computed based on the utility functions that are applied to the parameters that are associated to the edges in the pattern language, which basically then results in this kind of mathematical definitions, right? We have edge weights here. I won't like to deeper into that. And the other problem was, if I have a pattern identified that I need to apply, I dive into the working solutions, and we can even use utility functions to select the best, the most useful solution in this actual case. This is why we also have solution weights. So we call them solution weights, so the edges that connect the patterns with the solutions are also weighted, and no surprise, we are using utility functions for that purpose. Edge utility functions that steer us to make the proper decision to select out of the working solutions the optimal one. So, and then, in order to determine what the optimal paths are, we basically came up with the idea of utility function of the overall pattern graph, because often you have multiple potential solutions, and then you need to compare them. And for that problem, basically, we need to invent, to aggregate local utility functions into a global one. This is not yet solved. Right? This is what we discussed last summer. Right? So let's go ahead here. And the resulting abstraction basically is that it's a utility-based pattern graph. A lot of utility functions are there. Utility functions are smooth and concave in order to apply them. And the ongoing work is, so we have a draft of the algorithm to compute the solution path with maximum utility. Marina and I had some issues here, so we need to rephrase that. Then we are evaluating based on sample utility functions for a sample set of non-market properties. We have that, we are going to refine that, and this is all non-trivial, what I learned, and this is what Christos already liked, and we are going on and finish the paper, and so it's basically my part and else. But I also had to mention that I lost a friend, so I know Christos since 8 years, and we became a friend extremely fast, and I lost one of a few friends. Well, thank you. And the next one in line will be Leymann.
So I'm going to talk to you now in my capacity as the program director of the IMSA program, but also, of course, as a colleague of Christos and as a friend of Christos. And in fact, my prof will also want to be here, but unfortunately he has been ill, so we couldn't attend. So I'm also going to talk on his behalf. So, in fact, it's also with sadness in my heart that I'm talking to you right now. And we started IMSA together. So he was somehow the founding father of IMSA, also the godfather of IMSA. So he liked teaching a lot. He liked to be very close to the students. He was much closer to the students, in fact, than I was, for example. So in fact, he was IMSA. So he was cross-culture, he was cross-domain. So in fact, he was the T-shape that Frank just presented. I remember the selection meetings that we did have with the students. They were always fun to do. And he was always able to directly get to the person, to understand the person, and to select the best students in the cohort. He was also very accurate, was very precise, was very fast in responses. I remember our yearly dinners, Frank, with him, and also with Bernard, for example. He was very warm, he was a gentleman, I think, and this is something which is very special for us academics. And I cannot always find it back in all the colleagues. Doing research was really fun with him. So he challenged me. He was ambitious. He was very passionate. This is something which I like to see in researchers. He liked anecdotes. He liked anecdotes about him being a rector. He liked anecdotes about his time at Watson. He was very cosmopolite. He was everywhere. And that enabled him also to be the person he was. So I learned a lot from him. So I want to keep it very short, but at the same time I want to represent the students. So I'm going to finish my talk with 2 quotes from students. I remember him giving a speech in Stuttgart with a smile while explaining Greek methodology. I remember the first day he greeted us at the university, and also that he gave me a helping hand in the times we need. My prayers go out for him and his family. We will keep his memory alive by remembering the kind man we knew for too little time. The last one. It's hard to accept that in the end, death is the destination we all share. My deepest condolences to Professor Nikolaou's family and all of you guys, all his friends. He died, but his kindness and modesty will last forever in our memories. Thank you very much.
So we are not done yet. We have a speaker, last minute speaker, so to speak. In fact, he asked for a slot. So we have Professor Leymann. We will talk on this. Joanna, connect. Joanna, I do not.
I came here to, I knew Christos a long time ago, probably longer than most of the other speakers here except the family. I met him at IBM Research in the mid-80s. He worked in an office very close to the office of my ex-wife. And so when I would get out of her office, I would walk to his office. At the time, I was very fortunate to have Don Ferguson work with me on some ideas on how to use the economy as a blueprint to design computer systems. I was interested in building systems. It's interesting to compare that, and I'll soon do that, with the other talks here about service modeling. In service modeling, you start with an economic system and you try to formalize it in computer terms to study better how to run it. Our research was dual. We took the economic system as a model that we want to imitate in building large-scale distributed computing system. In the mid-80s, large-scale systems were born. I don't mean large mainframes, but large distributed systems. And they were not understood. It wasn't clear which disciplines would help guide us in building them. So the work that we did together should be viewed in that sense. It's difficult now to think about what was computing then when we have the computing now, but I connect the two. So this is in loving memory of Christos. So we try to see the economy as a blueprint for distributed systems. So we considered a very large transaction system and that is distributed with a lot of replicated database. It was even difficult to simulate. Something like that did not exist then. There were a transaction systems, but not on the scales that we were looking, tens of thousands of databases. But we wanted to see how far can we go with it. And so the idea was simple. We needed to deal with two issues. How do clients select which server they want to get the data from, that wants to transact with? And how do servers decide whether to replicate particular data or not? The economic approach was a simple idea. Why don't we have servers get paid by clients to provide the transaction? And the pricing would be according to supply and demand. So if there's a lot of demand to access particular data and there's not enough supply of it, then we'll up the price. The price reflects the imbalance between the supply and demand. So by working the price, we could balance them. And server leaves copies of the hot data to attract more transactions. We want to make more money. And there is competitive equilibrium where the supply and the demand are balanced. This is where the pricing clears the market. And this was a competitive equilibrium. At that time, we were thinking of how to coordinate distributed systems, not how to make them compete with each other. But if you think about it enough, competition is very powerful in creating greater robustness. If any one system component goes strange, the impact on the totality of them is minimal because they really see it as a competitor and do not rely on it. And the budgets of the client are used to differentiate quality of services. Surprisingly, it worked beautifully. I'll go to the results soon, but what the curve on the bottom show you is a citation from Google's Scholar of the paper from 1988. It's 30 years old work. Okay, so you see a wave here in the early 90s, and then another wave here starting in the early 2000s, and another wave coming now. And it's actually a strange behavior. Usually on Google Scholar you see a spike when the paper is published and then it goes down. Because after a few years, it's not important, people don't need it. These kind of waves represent different interested groups at different times. In the early 2000s, in the early 90s, in 2000, there was a great interest to understand the economics of the internet. So I think this is why we have this part of the wave. Then this interest declined a little bit, but then e-commerce became a big deal. And so the interest grew again. And then, what about now? I don't know. But I think it is related to growing use of economic ideas in design of systems. And I'll show you some of it. So I'll go now more quickly into this. This was our seminal work. The key surprise, one of the interesting things about this economic model, you do them, it's simple, but then you get surprised by what they do. And the surprise was that this was far superior for any number of systems that we simulated it, and for any other load balancing algorithm that existed at the time. Until today, we don't know how to explain it. But all our measurements showed that it was very fast. The convergence to the best economy and price was extremely fast. It was robust. It was stable. It was scalable. It had all these nice features that you would like to have. And it was a very simple and universal strategy to optimize distributed system performance using an invisible hand, the power of an invisible hand. Why does it work? Here's some brief explanation. I'll skip that. But it had subsequent impact. At that time, there were no other work like that. It was out of the blue idea. Within a few years, there were thousands of publications of other researchers that experimented with this. In fact, had even one or two conferences just devoted to that, and that Ramesh helped organize. So the second point of our interaction was, after the first paper, we began to study what others are doing, and that was when Ramesh was doing his PhD, and he was I was fortunate to have the opportunity to work with him because he was very productive and very influential, and tied Christos and me again and now Don also in collaboration. Just to tell you where Don has gone from there, he invented the WebSphere, which was a main web product of IBM, still is, and became one of the youngest IBM fellows ever. From there he went to computer stuff. After Microsoft, he became a distinguished engineer, and he's one of the only 2 people in the world that have been both. But he didn't want to stay there, so he eventually migrated. Now he's a CTO of their software. And so a lot of it started with through this work with Christos. And he was very influential on Don, Ramesh, and myself. Okay. So a little bit more, I'll go through some details because there's a point I want to get to which is important. And it's not so much trying to teach you technology, you've seen a lot of details now. So I'll just go very fast. If you look into the relationship between how much utilization you get out of a resource and what is the performance characteristics, it gets worse and worse. The higher you pressure the system, it becomes, you get long queue, congestion, delays, losses, also of bad behavior. So you can say that, on the other hand, if you stay in this region of very low utilization, remember, this is utilization, this is performance. If you stay in this region, you're underutilizing your resources. Now, in most of the data centers today, this is in fact the situation. And once virtualization was invented so that you don't stay here, and I'll talk about that in a second, but remember that point, that this is not where you want to be. It's very costly to be here and underutilized. You don't want to be here. You begin to suffer performance issues. You cannot assure the quality of the service. You want to be somewhere around. This is a region of desired state. The main question in how to optimize systems is how do we get them to be here and not to wander down here and not to be too far here. And that's a tough question, very tough. And there's no unclear answer, but there's a lot of effort by companies in academia to try to understand it. So with this I'll talk about, I started with the beginning, with the seminal paper. I'll now jump to today. This is a company, my fifth, that I co-founded. It's called VMware.com, and so far it's probably the most successful one, and it's entirely based on these economic ideas, and I'll show you how. So we think about, this is the IT stack. I think that one slide that was important. Okay, think about, this is the IT stack. You have some operating environment where with cooling and power supply in the room, and you have racks with hardware, and the hardware has CPU, memories, and so on. Then you have a hypervisor, which is a piece of software that images in some way the underlying hardware and make it and emulates it in software, so that the systems that run here think they're running talking to the CPU, but actually they're not talking to the CPU, they're talking to the hypervisor who allocates CPU for them according to some resource management discipline, so that they can flexibly be moved, for example, to other hardware in the middle of running. This is called live migration. So why would you want to do that if this particular hardware, this particular server is very, very busy, and a lot of them are running there, and there's another one that is empty, then you would want to shift the workload to the one that is empty. But to do that, you need to release all the ties, all the nuts that tie this thing to the hardware here. This is called the guest. It's an operating system and some application server. And it doesn't know what, and it couldn't tell us what CPU it's running on, as long as it's got enough of it. So this is the biggest transformation in data centers in many years. It actually was invented by IBM in the 70s, but popularized recently. And this is the basis of all current computing in data center. Now why? The main thing that existed before this was silos, big silos. Every group in an enterprise that wanted to run a service of some sort, run computing of some sort, would code and buy its own server hardware, would configure its own application, its own operating system, and manage it separately. Now, they need to provide enough capacity for the worst rainy day, the one where the spikes come in, the demand spikes. So you will get enough capacity to service a peak traffic. For example, if you run a retail store like Macy's, there are 3 days near Black Friday where more than 80% of the transaction, more than 60% of the transaction that you perform in a year, they happen through 3 days. You have to have enough capacity for these 3 days, but for the rest of the year, you're not using it. So you're wasting most of the capacity most of the time. And at the same time, during the peak traffic, you may not have enough because you didn't budget enough. So this was a problem before. And virtualization permits you to spread the demand and mix and change different applications and serve them. When I have a peak, some of the other application has bought that row. So we can use that so that I get the capacity when I have a peak and you get the capacity when you have a peak. And that's the main thing that virtualization does, evens out the resource uses and makes it more efficient. So you don't stay in the region, blue region with very low utilization for most of the application most of the time. And then you jump to the red region where you don't want to be when the peaks arrive. And that's how data centers are managed today. So what does it have to do with economy? You can look at this hierarchy called a T-stack as a supply chain. It's each layer, the value of each layer is to the layers above it that consume the resources provided below. So the applications, they want to run in some guest operating system and execute what they want. So they get a budget from the business in virtual currency that reflects the value of running that application. They pass the payment to pay for their CPU, memory, and storage to a virtual machine, this orange piece here, which is in the hypervisor. The hypervisor gives them a virtual machine, and they pay the virtual machine for the resources they want to get. The virtual machine has to pay the hardware, the servers, the host, for each resources. So they pay for CPU, memory, and however much it wants. But the servers themselves have to pay for the operating environment, for the power, for the cooling. So you can use this paradigm to take this IT stack and decompose it into its component, and then associate payments flowing from each layer to each layer. So the value flows bottom up, and the payments flow top down. And if this economy is stabilized, which was a big if when we started the company, but now we know it does very well so. And again, we're not always sure why, but it's amazing. So we just pray that it continues always. But we have sometimes good explanation. But this is very stable economy, and it tends to optimize very quickly the relationship between consumption, between demand and supply. So when workloads come in and they change, and they can change dynamically very fast, the allocation of resources which track these changes, and we may move every 10 minutes some machines to new hardware so that they get enough resources and do other actions to balance the supply and demand to the invisible hand of the supply supply chain economy. So everybody in this economy pays for something, but get something from something above it, and it creates a balance both ways. Now the budget will differentiate services, so if this is very important application for Macy's, it's got big budget, it will find a way to buy its way even when the system is highly loaded and the prices go up. If it's not an important one, it may be set to wait more time before it gets allocation of resources. So there are surprises in this, and I'll show you one surprise that surprised us. We accidentally hit it when we wrote our first patent, and fortunately so, but it was completely a complete accident. So this is a problem. If this is the typical data center network, one architecture. It's hierarchical, so you have multiple layers. This is the core, this is the aggregation layer, this is top of the arc switches for those of you who know what it means. And you get two virtual machines. This is all virtualized. So the virtualization is here. Each one of these is a host. And you get two virtual machines, and they talk to each other a lot. Maybe it's called sometimes elephant flow. So this is small elephant flow, big elephant flow. But there's a flow between these two virtual machines, and you need to place them somewhere in this network so that you can service this flow. So suppose you randomly place them. One of them goes here, and one of them goes here. So what would this mean? This is pretty much how it's done today. They're randomly placed. It means that the path between them, where all the communication, heavy-duty communication go on, will have to go all the way to the top of the tree and then down. And if you have 100 ports here, the probability that this will happen, if you randomly put them down, is 99.9%. So most of the flows in the data center will go right smack to the top and create huge congestion and delays and lost packets and bad latency. And in addition, it's very costly because the cost of these switches, which are 40 gigabits, becoming 40 gigabits now, each time you go to a switch, you're spending the amount of money twice as much as you go on a server, because it's twice as costly. And if you go to many of them, if you go close to here you would need 100 gigabits soon, already in many networks, and even more so into the future, if we continue this silly way of placing them, where you ignore completely the network and making decision how to allocate resources to the virtual machine. So what is the surprise? The not surprise is that there's a better way to serve them. Suppose you can put both of them in the same box, on the same blade in the rack. So now they're talking to memory. They write a packet into some place. One of them writes a packet into some place in memory, and the hypervisor moves a pointer to this memory to the other. So that's all it takes. This is zero latency, practically. Infinite bandwidth. You cannot beat it. And you're not using any port on this that costs money on this in this network. So fantastic. Why can't we do that? For a very simple reason. If we put all of them on one blade, then we can run. There's not enough resources. So there's a competition here between how many resources do we have in the network passes, and how do we balance between the allocation of communication passes and memory resources and I/O resources and CPU resources. You need to find some balance that would be meaningful. And the economy is exactly what gives you the ability to do that. So how does the economy work here? And this is a surprise. Surprising if it works. Let's try the economy. So what are we going to do? We need to put the price. What do we price here? The resource. What is the resource? The path that you go through. So if you go to this path, obviously you have to pay a lot because you are causing a lot of trouble for everyone. You're interfering with them, you're creating congestion, you're using the resources in the wrong way. And if you do this, the price can be zero, because you're not consuming anything. So what if we set the price to be proportional to the number of switchboards that you're traversing? And then we run the economy. So for us, it's just one more resource. And it has a simple pricing mechanism, and lo and behold, it works. It does a phenomenal job of placing the, these virtual machines and optimizing the use of all resources in proportional way. And this is very powerful, because if you wanted to run an algorithm that does that, not only is this problem algorithmically very hard and to complete, any approximation that has been proposed will take you hours to run for even a simple system, and you don't have these hours to make the decision. You have to make it fast. So we built it in a company. We have product, but I'll tell you briefly about the company. It's very rapid growth. 2 years ago, on January, we have a company meeting for everybody. 2 years ago, there were 45 people in the meeting, which was great. We were beginning to sell and market, and then a year later, it was 93, and then this year it was 217, and now it's already 480, but actually nobody knows how many people work in the company. I think maybe somebody knows, but I'm not sure who, because we expand so rapidly. And the company is extremely successful because of the first fact. We do such good resource utilization. I'll go back to the slide and tell you about that in a second. We improved their utilization by 35% while assuring the performance. And that's worth a whole year of budget, of IT budget for some. So, and everything is doubling every year, and this is all some awards. But I want to go back and say where is that on the pictures that I showed. It all goes back to the seminal paper we did in the 80s. And this was a traditional trade-off care, except there are multiple resources here, not one, so it should be multi-dimensional. But the point is that when we could shift the utilization from this region to virtualization to this one, but prevent it from going this way by pricing the boundary. So the closer you get here to the danger curve, the higher the prices, and therefore you could never cross it. There is a real barrier here that we set to you. We hunt you into this region. Now, in this region, which is a safe region to run the system, there are no failures. It's secure, relatively, not in the sense of security, but in the sense of robustness. And it's very efficient. You're using the resources that you can use without causing trouble, and you can guarantee the performance. And so it all goes back to this idea in the 80s that we had, that maybe the economy can provide a nice blueprint, and the invisible hand can work for us, and surprise us that it works. And it does. It works, and it's surprising. And we then try to understand what is it doing. And we tried to do it 30 years ago. We tried to understand why it's working. And we figure out a little bit, and we're still trying, and we figure out a little bit, but it works beautifully. So I owe it to Christos that we had a great opportunity to collaborate and sharing the garden with the students, and I love our interaction. And still remember the meeting, so I made all this effort to come here and share this occasion. Thank you. Thank you.
So this ends the. Now I can speak loud. So this ends the morning session. We continue at 3 o'clock in the afternoon, because the intent of summer school is to communicate with each other. This is why we always have at least 2 hours was the communication. So we continue at 3 o'clock. Wolfgang will be the session chair, and we start with a paper session, because this year at SummerSOC we changed SummerSOC a little bit, because we invited submissions of paper, we had a review process. Some of the papers got selected, and we start always in the afternoon with a 3-hour session on presenting the papers, and in the morning we have the tutorials. So we start at 3 o'clock again. And for those of you who belong to the directors of the summer school, please remember that we meet at 1 o'clock at the, Tim, was it 1 o'clock? Yes, the director's lunch?
1.
Okay, so we meet at 1 o'clock down at the beach bar. So, see you back at 3 o'clock.
Stay.